Okay, welcome to Unit 3, and in particular, the practice exercise 3 that we'll be looking at today. We're going to start talking about linear regression, one of the most basic methods for predicting data. If you remember from your overview of machine learning, there are two kind of types of supervised learning: regression and classification. Regression tries to predict numeric values, and classification tries to group things into distinct categories. We're going to be looking at regression in this unit. So here's the start of practice 3. We'll go through this code. So the first thing we do, we're going to set up some libraries. These are common tools we'll now be using in almost every notebook that we have. So we import pandas and numpy. These are two well-known machine learn or data analysis libraries. Pandas helps us read in comma separated values fields, gives us our data frames, and NumPy is for multidimensional data and linear algebra stuff. And then we do two graphing things: math plot and Seaborn. So this just implements those. Some of these give a couple errors, so we just turn off some of the warnings here. You don't need to do this, but it just makes it a little cleaner for beginning users. Then we're going to import some data here. The data comes from this house sales in Kings County. House sales is a common challenge for regression and a common data set. So this is a data set from Kaggle. If you click on it, you'll go here and you can see the columns. So every house is given ID, the date the house is sold, and then the price of the house. We have things like the number of bedrooms, bathrooms, the square feet of living area in the house, the lot size, number of floors, if there's a waterfront view, or if it's on the waterfront, if there's a view of the waterfront, condition, grade of the house, year it was built, zip code, longitude, latitude, and then some living for some living room areas here. We're going to use a number of these features here. Now, just so you know, Kings County is a county where Seattle is, home of Microsoft, Amazon, and etc. And so it tends to be an expensive housing market for us. So you'll see a lot of expensive houses. My daughter's right now living right out here in Seattle, just renting an apartment, and I can agree it is very expensive for her to live out there. Another thing, that you might want to look at if you're curious is on all of these Kaggle things, there are always a discussion and a set of kernels. Lots of people will post their own example kernels, or kernels are the Kaggle version of notebooks, their own notebooks that look and predict and work with this data in different ways. Okay, but we don't have to worry about that. Okay, so we're using this data and we're importing it into here. We're reading it in. I have two versions, one that reads 1,000 houses and one that reads 250. I think we're going to go with this 1,000 house version of the data that we're going to read in. The actual data is more than 20,000 houses, but for our work, we don't really need to use that full data set here. So we're going to use only the first 1,000 houses here. Now, just a note, what I did originally is I actually tried to use Stack Overflow's salary data here and brought that in. And Stack Overflow is a website that collects a whole bunch of salary information from IT workers across the world. But it's interesting, there weren't very good correlations in that data. For example, the amount of education or the amount of time at a job is not a good predictor, according to that data, of how much your salary is. Okay, so here we're bringing in the data. So, oops, I want to start running these cells. Run this, bring in the data. Again, here's the first couple lines. We can ignore this date of the house, the price of the house here. is often between 200,000 and a million, a couple million dollars. And again, bedrooms, bathrooms, living space in square foot, lot, floors, that sort of stuff. One thing that's nice is, most of this is numeric data that we have. And also the price, this is what we were predicting. This is numeric. So this is why it's a regression problem. We're trying to predict a numeric value given some other numeric values. Initially, I'm going to drop a whole set of columns here just to make it a little easier. The date, we're going to assume the date is not important. Also, the latitude and longitude we're going to assume is not important. And then the year renovated and the square foot stuff, I'm just going to drop that to kind of simplify things. We have the square foot measurements duplicated into other places in this data set. So after I drop this, if I go up here and do the house, the header again, you can see it is just dropped. But we still have quite a few columns here to look at. Okay, now let's talk about correlation. We're going to be working with linear regression looking for these correlations. Correlation is a measure of how related two values are from this. For example, here I'm going to scroll onto this graph first. This is a graph, what is called a scatter plot. Every dot is a house from our database. And along this x-axis is the square feet, and along this axis is the price. And you would expect a house with more square feet to be more expensive, and this data kind of shows that trend up here. So a small house might be only 800 square feet, so that would be like 800 would be about right here, and you can see there may be $200,000 to maybe $400,000 in that range, where a larger house might be a really nice large house, might be 3,500 square feet. So again, right between 3 and 4,000. And if I go up here, I get see you can still get some houses around $500,000 for that, but more of them are up here towards $1 million, and some of them are even more than that for that price. So there's a correlation between the square foot of a house and the price that we're looking at. And we measure that with something called a correlation coefficient. The question is, how strong is that relationship? And so certainly not all houses are. If you know the square foot, you can't exactly predict the price here. Again, for a 3,500 square foot house, some of them are way down here, but there are some that are way up here. So it's impossible to predict, but there is some relationship here. Generally, when we look at data, if they're not correlated, they'll just be spread all over the map or all over the graph and no lines. But if they're correlated or even more correlated, they should lie among a band, generally one way or the other. This might have different kind of slopes, it could be at different angles, but again, there should be this linear clump of data showing that, if you know some value on x-axis, you can predict the value along the y-axis of this data. And in the best case, it's all very clumped together here. And so if you know an x-axis, you can predict really well. This correlation coefficient goes between 1 and -1. 0 meaning there's no correlation. 1 or +1 means there's either a strong positive or negative correlation. Both of them are fine, and we can predict the data with either one. Here. So a correlation of 0.4 is not, we can do some predictions, but not much. Correlation of 0.8 is really quite good. If we see this in our data, we're often very happy and we can predict things. Now, correlations, don't worry too much about the slope. And again, there's lots of ways that data could be correlated. It could be clumps and stuff like that, and it won't be picked up by this correlation coefficient, and also linear regression will not work. So if our data scatter plots look anything like this, linear regression will not work. We want plots kind of like this for linear regression to work. And so it is somewhat limited in its scope. There are some other types of regression that sometimes can do this, but we won't be looking at those. So as we mentioned, the house prices here are plotted with square foot ring price. And again, we can use linear regression then to try to draw this line here it calculates, averages out where all these dots are, and tries to find the line that is the best fit for all the dots, so that the distance from each dot to the line is the least. If we move this line at a different angle or up or down, then the distance from all the dots to the line will increase, will get worse. So it finds, calculates that. And we're not going to go on how that's calculated for that. And you may ask why. And there are a lot of machine learning classes will teach you how to calculate this. And I just don't think it's that important to know how that's calculated these days. When I first learned to program, I was taught how to calculate the square root of numbers using math, using the algorithms for calculating square root. But that was in high school. But by the time I got to college, I was told never to program in the square root. You should always be using the square root function. All the languages by the time I got to college had a square root function, and I can't imagine you probably don't even know how to calculate a square root. You've always used the square root function on a calculator or something like that. Similarly, I was in college. I was taught algorithms to sort data in different ways, and taught different ways to program those, and told you that every time that we'd be using those frequently in life. But by the time I got out through grad school and in my first job, I was told, no, you should never write your own sorting algorithm, that we have pre-built sorting algorithms now, and we should always be using those. And so today we do teach a little bit of sorting, but we tell students that they should be using the sorting algorithm. I think linear regression is simpler or similar. It's important to know what linear regression does. It does calculate the distance of every dot to this line and minimize that so that it finds the correct line here. But you don't need to know the algorithm to actually do that, to make use of it. So, okay, but your first task is to understand what the correlation component does. So look through this graph, understand these, and put your answers in here. The first thing I want you to do is estimate what would a house be. So if you look at this line here, you could look at this data, but you have to kind of approximate. It's probably easier to look at this line. So if you look at a house with 4,000 square feet, you go over, well, first a house with 2,000 square feet. If I go over to 2,000 square feet, there's a nice line here, and I go up, that house should be worth about $500,000, $500,000. And again, your job is to look at what would a house at 4,000 and 6,000 square feet be according to this linear regression line. And then describe something about this correlation coefficient. So once you've gone through that, we'll do the linear regression model. We use this Scikit learning library. This is another library we'll actually be using quite frequently to import our regression model. And you can actually click on this if you want to learn more about this linear regression model and how it works. Or if you're interested in the whole Scikit library, there's details. They have lots of different things here. Again, but we'll be jumping in and using that quite a bit throughout this course. So when we create these models, we often use two variables, x and y, and sometimes x is in uppercase and y is in lowercase, just because of practice. And so x will always be our input data, and in this case, x is along here, and again, this is the x-axis, is the square foot, and then y will be the output, will be the price. So given the square feet, can you predict the price? Here. So we'll use these two variables a lot in our analysis, not only in this week, but in future units. So we're setting up X, and again, this what we've done above here is, remember, we created a data frame, which is again this like array-like structure to hold our data, and we just called it house underscore df for house data frame. So we can use that in our code here. So we're using house data frame, and we're grabbing one of the columns out of it, the square foot, and we have to do some work to reshape that. You can not worry about that. And again, the price, we're using the house data frame and the price, and again, we have to do some formatting to turn that into a simple array of numbers for our machine to work with. So we're getting the square foot as the x and the price as the y. And then we're going to create a linear regression model. And again, from our SK Learning library, we imported linear model, and from that we are creating a linear regression model, and we just give it some name. And then we can use that model and we call fit. And what that does is do what we described above, is figure out this line, calculate where this line will be given all the data points. So in this data set, there's 1,000 data points. It has to find what's the best fit for that line for that 1,000 data points. So this might take a little bit to run here and work. So if I run this, again, it takes a little bit to find that. Again, if we were using the full data set with 20,000 data points, it would take even longer to run for that. So once that's run, we can use that model to predict. Just like you were manually predicting what's a 2,000 square foot house costing, you were saying looks like maybe a little bit above 500,000 here. We can now do that exactly. We can use our model variable that we created up here, use that, and there's a method called predict, and we can predict a value. Usually provided a list of values, and so it's kind of weird we have to do this double brackets for a list here, but we can put 2,000 in here and get a prediction out. And here's the prediction we get. Is we store that in this prediction variable, and then we print it out. It's not formatted very well, but this is, $500,000.70 basically for that. So that's our prediction there. And again, we could change this if we wanted to do a different prediction. Let's say we wanted to predict what a 3,000 square foot home would. We would predict that, and that's coming up to $776,000 house for that. So your job is then to, for task 2, is to predict for 4,000 and 6,000 square feet and compare those to what when you just looked at the line, what you estimated up here. So put those predictions in here below this line. What your model actually predicts, and then what you had kind of guessed above for those values. Now just quick, there are some bonus challenges I'll throw in every once in a while. So this is not formatted very well. So if you want, you can do this bonus challenge to try to get it to format like this. And look at that. It's not required, but again, if you're just interested, if it just bothers you that it's not formatted, you're certainly able. This is we'll show you. Look at that. Also, when you're looking at posting things to the discussion boards, posting solutions to the bonus challenge and stuff like that are good ideas of things to post, or even wanting help with the bonus challenge is a good thing to predict. Okay. So how do we know how good our predictions are? Is this a good prediction of this house? How accurate is this prediction is? So we're going to look at how we can test out these predictions. So in order to test out our predictions, we're going to go through our data and split it into a training set and a testing set. So we're going to set aside maybe like 20% of our data as testing data, and then we're going to use the remaining 80% to train or fit our model. And then once we have our model set, we'll use that. We'll run the testing data through it and see how accurately it predicts. Because in the testing set, we know the square foot and we know the price, and then we can measure how accurately it predicts the price. And what we always want to do is make sure that when we have a testing set, we never train or fit or use that to create our model. We only use data in our training set to train the model or fit the model. So now we could just grab the first 80 or 20% of the data frame. So up here we have a data frame, and remember in unit I think 2 we looked at how to grab just certain rows out of the data frame. We could just grab the first 200 rows from our data frame and use that as our testing data. But the data might be sorted somehow, or there might be some issues with that. So whenever we do that, we generally want to randomly select houses for testing rather than just grabbing the first 100 houses or something like that. And this is very common. We call it a train test split of our data, and so it's built into our sklearn library here. So this is how we do that. Let me run this. So we do have to do an import of this from the library, something our train test split method, and then we call train test split. We give it the x and the y value, and then we tell it, in this case, how much of a test size to have. And I'm saying we want 20% of the data set aside for testing, and it will give us four things: an X for training, an X for testing, a Y for training, and a Y for testing. So this will be the first, like, let's say if there's 1,000 houses here, this will be 800 houses, and this will 800 house square feet spots. This will be 800 prices, and this will be for testing 200 and 200, the square foot and the price of those houses. So we have those variables all set up. And now we can fit our model. And again, now when we want to fit, we only want to use our training data. We don't want to use our testing data here. We just use our training data. And again, that will look at the model, look at the square foot and the price, and try to figure out what this line is and calculate what the line is. We can actually get the slope and intercept and all that stuff from the line, but again, we're not going to worry too much about that in this course today. So we fit our model with that training and testing data, and now we can score the model here. And it should give us a number between 0 and 1, although sometimes it may be negative, but usually it's between 0 and 1. 1 is perfect score, meaning 100% of the time you can predict the price of the house exactly right all the time. Score 45 is less accurate there, so it's not. It uses, again, I'm not going to go too much into it. It uses something called R squared prediction, and it's quite complicated how it calculates the score. But just know that it's a measurement, and a score of 1 is the best score, and a score of 0 is bad. So now when we run this, like right now, this last time I ran it, it gave me a 0.45 value. And if I run it again, oh, this time it got a little better, got 5.1. I can actually run this again and get different values. Every time I do let's go back up here. Every time I do the train test split, again, it randomly selects houses, and again, I can train it and then test it, and I'll get slightly different results because, again, it's randomly picking some houses for training and some houses for testing, and that will kind of, depending on what houses I can see, it will change how accurately I can predict the other houses for that. Okay, so now your job is to improve this model some. So we're going to take all this code and put it down here all together. So we're grabbing the X and the Y, square foot and price. We're then using a trained test split from the X and Y. We're then fitting the model, and then we're scoring the model, and then we're putting out that score. We're all doing that all here. But your job is to look at some of these other values. So up here, we are looking at square foot to price, but maybe the number of bedrooms is a good predictor, and try to think in your mind, what is a good predictor of a house value here? Is it the condition? Is it the grade? Is it the size of the basement? Is it the year it was born? Is it the zip code? Which of these? So try some of these different values. So I've listed out the values there so you don't have to keep scrolling up and down here. So maybe I would think the zip code is a good location, what they say in realty. So I could try the zip code here and run that. But zip code is not a good predictor. Just knowing the numeric zip code does not help you. Zip code, you'd have to add some other data here, like maybe what is the crime rate per zip code or something like that. Rather than the zip code. So this is a bad score. So again, you want to try out a couple different scores and describe. So what you need to do, there's two cells here. Try two different values here and there. And then also go through, I want you to kind of understand this code a little bit. So go through and write up here in part 2 full sentences. So part 1 is to try out two different features from the list, like zip code and something else, but maybe zip code's not the best choice, so pick two different other ones. And in part two, then try to describe what this code does. Try to describe it in full sentences up here, what each line of the code does, and see if you've understood what this code is doing somewhat. Okay, so that's part task 3 here. Now you might think, well, is there a better way? I don't know houses that well. Is there a better way to predict, to choose which features to use? So there are some ways. We can look at the correlation coefficient here. And so this is a graph of the different correlation coefficients. This first column is the price, and the price is also here, and this. So if I look at this first column, which is the price, this is the correlation between the zip code and the price. And I notice it's not very good. It's 0.06. It's actually negative. Similar for the year built, but things like the square foot of the basement or the square foot above ground, the grade of the house is important, it looks like. So if I look at my scale, anything that's up here, dark red or dark blue, are good values. So these are good values. Even the view, whether or not it has a view of the waterfront, the living area, the number of bathrooms, bedrooms, all these are pretty good. And of course, if you know the price, you can predict the price with 100% accuracy here. So basically, you can just look at the first column, the price column, and how it relates to each of these other columns here. Another way is look at is this graph, which shows all these correlations also. Let me see if I can get this on the screen a little better. So I'm going to go over to the left and go down to the bottom. So similar to above, in my little view here I'm recording, it's hard to see this, but this is the price. So this is the price per square foot living area, price per longitude, latitude. So these are all the price variables here. It looks like I hadn't updated that graph, so I'm just running this code again. And again, to calculate all these correlational matrices and our graphs, it just takes a sec to run on our machines. So as we can see, the price and the zip code correlation is not very good, not very clean here. We want something like this, where we can kind of see a line of some sort, where we see some sort of prediction. You can see the grade of the house has the condition of the house has some impact. The number of floors, it's hard to say, but there. So again, you can look at this. This is our square foot living. That does seem to have a good correlation here. So is the number of bathrooms, even more than bedrooms. So again, you can look at this and get ideas and predict that. And once you've looked through that, we can actually use multiple features. So we can do a multiple linear regressions here. In the code here, we create a list of parameters, so like square foot and floors and waterfront, and then we use those parameters to create our X. So now our X is not just one feature, but is multiple features, and then we can score our thing. And now we're getting a score of about 0.51 on this. So multiple features, we can combine multiple features and do what is called multidimensional linear regression. So it looks at multiple features in the x-axis to predict one feature along the y-axis here. Now, if using a couple features is better. So the last thing we're going to look at is using all the features. So here, this is using our feature data frame. Here our feature data frame. Here we're creating a feature data frame, but we're just using the whole house, all the features in the house data frame. And then we're doing some formatting of that, and then again, train, test, split, fit it using the X and Y stuff, and then test it using the X and Y test data and print out the score. And if we run this, amazingly, we do really, really well using all the data in the frame. Gives us a score of 1, like perfect. So if we know all the features, does that make sense? So task 4, you have to find the error in the code. A score of 1 is basically impossible. So you cannot perfectly predict the house price given the features. And so I want you to describe in English why you shouldn't be able to perfectly predict the house price given its features here. And then we're going to fix the error here. So our error is that we are actually um, in our model, we are including the price of the model. And if you know the price of the model, you can perfectly predict the price of the model. That makes sense here. So we accidentally are using the when we're using this, we're using the price of it. So your job is to take this line and replace it. I'm just going to, let me click on this line and copy it and go up here and replace. I'm just going to put a comment. If I put a pound sign in front of that line, it'll comment it out so it makes it so it doesn't run. And now I can put this line in its place. So now we're grabbing the house data frame, but we're dropping the price column here. Axis 1 just means column wise. So we're dropping the price. So our feature data frame is just all the fields, all the features in the house data frame minus dropping the price one. And then we're using that as our X features, and the price is now our Y features. So if you run this, you will not get your 1.0. You'll get a different number here. And again, now there's some randomness built into this, so we want you, after you fix this error, to run it multiple times, and then to describe why you're getting, put the answers, run it 3 times, put 3 scores here, and then describe again where's the randomness coming and why do you get 3 different answers when you run this 3 different times. So that wraps up our details on this practice activity and your introduction to linear regression and correlation.